Morning. I'm going to essentially carry on from where Bill left off in many respects. Stickney crater is like a lot of craters on a lot of bodies. They all seem to get one big one somehow. Stickney crater is an important crater for Phobos because there's really, the history of Phobos is before Stickney and after Stickney. It's a major event, and Stickney itself apparently contributed quite a bit of its own history. So with that, we'll start with my roadmap. I want to talk about ejecta from the Stickney crater. Ejecta from an asteroid will go off into solar orbits and become part of debris in solar orbits, but ejecta from Stickney crater, most of that returns to Phobos. So I want to talk about that a little bit. I also want to talk about what happens because of the impact itself. I have my little model of Phobos. And it looks like what happens is that Phobos is currently in a tidal lock, typically in a tidal lock orbit around Mars, but the impact will break that, will desynchronize that tidal lock. And I want to talk about that some. And I also want to talk about the amount of time that it takes for that tidal lock to be restored, because if you have debris trapped in orbit around Mars and it's impacting Phobos, if Phobos returns to a tidal lock immediately, then all of that debris ends up on one hemisphere of Phobos, and if Phobos continues to be desynchronized over a long period of time, the returning ejecta will impact Phobos on all of its longitudes. And the last part I want to talk about is just some of the effects that we see as a consequence of these secondary impacts. So first I want to show you a 1-minute video, and what this video is from my physics model. Our physics model, it is not an impact. What it is it's a radial distribution of ejecta coming from Phobos at its current orbital altitude, 800 meters per second, which is a little bit on the high side, but it's really good for illustrating what happens to this ejecta after any impact on Phobos. So let's see if the movie will start. Yeah. So here's I'm sorry, wrong button. Yeah, I just did that. Okay, so radial distribution, all directions. The brighter orange colors are higher orbital velocity with respect to Mars, and the green, bluish are lower velocities. And what you'll notice immediately is that from the leading hemisphere of Phobos, it races ahead, it starts to gain altitude. That's because the velocity of the ejecta combines with the velocity of the orbit of Phobos, so it goes into higher orbits. And in the same way, the lower velocity combination of the orbital velocity of Phobos and ejecta produces smaller orbits. And some of this is actually intersecting Mars itself. Now, a really, really interesting thing we notice here is, look at this, right here. Everything's coming back to the point of impact. We call that returning to the scene of the crime. It's something we see in orbital mechanics when we're doing spacecraft engineering. You change an orbit, the old and the new orbit intersect at the point of the change. So every single thing that gets trapped in orbit around Mars as a consequence of an impact, as long as it doesn't go off into solar orbit or impact on Mars itself, it returns to the scene of the crime, and it will impact onto Phobos. So the question is, well, how much is there? How much material is there? And when we look at all launch velocities of all ejecta from Phobos, about 40% of the leading hemisphere impacts will end up in solar orbits, and about 10% of the trailing hemisphere impacts will end up on Mars. So another way of looking at that, about somewhere between 60 and 90% of the ejecta that exits from an impact on Phobos returns to Phobos. Now, according to the literature, that happens within about a million orbits, or around 1,000 years. And because of the preferential nature of the process, where Phobos, the orbit precesses, the material precesses, or whatever, most of that material returns within the first 100 or 200 years. Okay, so where does it end up? Another quirk of orbital mechanics is if you have an impact on one side of Phobos, it exits going in this direction, eventually comes around, and it will impact on the opposite hemisphere. So all the trailing hemisphere impacts, all of that material will end up on the leading hemisphere, and in the same way, leading hemisphere ejecta will end up on the trailing hemisphere. Okay, so the question I really wanted to ask, wanted to know is, well, first of all, what happens to Phobos as a consequence of the impact? I want to know, where does this material end up? If Phobos it remains tidally locked, well, we know that all of the Stickney ejecta is going to end up on the opposite hemisphere. If Phobos, the tidal lock is broken, it could be uniformly distributed, but if that tidal lock is only broken for a year or two, it still ends up in just one hemisphere. But if it turns out that the tidal lock is broken for many, many hundreds of years or thousands of years, then Phobos continues to rotate like a rotisserie chicken and continues to accumulate debris from orbit. So the question is, does it break? Is the first part of the question. And it turns out that indeed, okay, here's Phobos in its natural libration system. It's tidally locked. The Phobos itself is reasonably represented as a tri-axial ellipsoid with a long axis that oriented towards Mars. So it's either oriented this way or it could be oriented 180 degrees the other way. And it rotates on its axis on the shortest axis, the c-axis. So the question I have is, okay, how do you desynchronize the tidal lock of Phobos? And the first way you can do it is you can compress material into Phobos. You can just take the same mass, push it towards the center of gravity, and that will change the moment of inertia, and just by the math, it will increase the rotation rate of Phobos. The two other ways is you can change the angular momentum of Phobos. Either you can add energy to the orbit, changing the angular momentum of the orbit, and if you have a tidal lock is the relationship of the orbital period to the rotation period. So if you accelerate or decelerate the orbit, that desynchronizes the tidal lock. Or you can directly change the orbital period. So the question is, okay, well, Phobos is getting this impact. It's getting this impulse. How much energy is that? And there's a couple of ways, or what is the mechanical effect of that? And there are two ways to look at that. One is you can try to estimate how much ejecta comes out of the crater, what's the velocity of the ejecta, and then you can try to do a calculation based on that. We do that as a double check. But what I did is I took something similar to what Bill was talking about, estimating the size of the projectile and the projectile velocity, and that gives you how much energy there is. And we can put that into the Teleskowsky ideal rocket equation and calculate an exact force, well, exact as far as we can estimate what the factors are. So when we do that, okay, of course, it's not a rocket engine; it's a crater, and craters, obviously, are not as efficient as rocket engines, but they do produce ejecta with a certain velocity, so that's where most of the flow is, most of the impulse is coming from, and some other sources. And then there are all kinds of inefficiencies: melting, fracturing, heating, compression that is lateral, and so forth. And when we factor in all of the inefficiencies, our rocket engine's about 60% efficient, and the total acceleration impulse is about 1 meter per second. Okay, so we partition this, and I already talked about changing the moment of inertia. When we partition all of that, we get about 10% of the desynchronizing effect due to the compression. We get very little due to changing the orbit, even though most of the energy goes into changing the orbit has so much angular momentum that it's an inconsequential amount. By far, the majority of the change has to do with a direct impulse that changes the rotation of Phobos. Now, most bodies that wouldn't be the case, but Phobos has this, Stickney has this odd location. It's on a westward-leaning hillside of Phobos, and the orientation of the crater is offset from the center of gravity, so that gives you a lateral impulse. It's also sitting right on the equator. Okay, so depending upon the orbital history of Phobos, it'll have a different effect if you're closer to Mars or further away from Mars. According to these calculations, we get about 1 extra rotation of Phobos for every 3 orbits or so, something like that. So it's a considerable amount of desynchronization. So the next question is, well, how long does that last? And there's an equation, Gladman et al., and when we plug in what we know about Phobos and our estimates of Q and so forth, all the different factors, at least, we're talking at least 5,000 years before the desynchronization comes back into a tidal lock. Now, what I was talking about before is that the ejecta is returning within 1,000 years, probably most of it within 200 years, and we have a desynchronization of about 5,000 years. So that suggests strongly that Phobos is, the entire surface of Phobos is exposed to secondary impacts, ejecta returning from orbit from Stickney crater. Okay, so the last thing I really want to look at is what are some of the consequences of this? What are we going to see here? And there, the first thing we'll see is it would make a great movie. Every orbit for 18 seconds, you have this enormous storm of impacts, because that's the only place that these impacts are going to happen. So when we do size frequency distribution, the red is during the first 10 years, and that tapers off over time. When we look at the final consequence, we have a huge number of craters. There's just a lot of material. It's either a lot of little craters, a lot of medium craters, whatever, but ultimately it's really hard to work out any size frequency distribution that doesn't produce at least 2 craters 400 to 800 meters in diameter every square meter on Phobos from secondary impacts. So we're seeing a huge, huge effect. And it makes sense because Phobos is a really small body. It's not like the moon where secondary craters can go off into, we never see them again. It all gets concentrated in a small surface area. Okay, so this is from Schmiedemann et al., and he worked out he did size frequency distribution crater counting. This is just to the west of Stickney crater. And the blue right here, the blue line is a size frequency distribution of secondary impacts from our model from Stickney crater. And the red is the crater counting that we're seeing west of Stickney crater. And this area right here are the background craters, the big background craters. And then there's this kink, and all of a sudden it kind of lines up with what we're seeing for secondary impacts. So we suspect very strongly that the kink we're seeing here is from the secondaries that we predict. And when we look inside Stickney, we don't see the kink. All we see is a size frequency distribution for the most part, except for a couple of big craters. For the most part, it's consistent with secondary impacts. So it looks like most of the craters inside Stickney crater are secondary impacts from Stickney crater. Okay, so what is that? What are the consequences of that? Well, the obvious consequence is that we can't use craters to date Stickney craters because we're looking inside Stickney and we're seeing secondary impacts from Stickney. I say it suggests that it's a recent event. Well, it suggests that it could be a recent event. It could be a slightly older event, but we can't date it from craters at any rate. And the last thing is that in no part of Phobos can be dated with craters that are a kilometer or so in diameter and smaller. So this is my last slide. So then how could we possibly date Stickney crater? And we really have two possible other parameters. One is space weathering, because space weathering takes a certain amount of time, and apparently Stickney crater is space weathered pretty much as the rest of Phobos. So, okay, at least 100 million years from that parameter. And we also find boulders on the rim of Stickney crater that, according to Basilowski and et al., would be destroyed within about 500 million years. So that's the one that we really look at. If we can really date these craters, these boulders, then we'll probably get an age for Stickney crater. So with that, I will take your questions.
Your upper limit on the age of Stickney from the boulders seems inconsistent with Bill Baki's statement that one Stickney crater will be produced since the Martian hemispheric dichotomy was produced 4.5 billion years ago, and most of the bombardment during that period would be prior to 4 billion years ago. So it'd be extremely unlikely. And I want to see how these two things can be rectified.
Well, what's unlikely, it's not impossible. It's not, the boulders are there. You have to account for them. You can't just say that these boulders, because you can't say they lasted 3 billion years. We're not going to find boulders that last 3 billion years or even 2 billion years. So it's the boulder evidence that we really have to be looking at. That's what sets the upper limit. Unless you can account for the boulder some other way. But I agree that it's far more likely to have a giant crater in the past. I mean, absolutely. I totally agree. I have resisted in equal measure. So anyhow.
I'm sorry. You went a bit quickly over the the model of getting out of tidal lock. And of course, there's an intermediate stage, which would be to increase the libration amplitude, giving it a free component that would then damp away again. And in fact, even when you're despinning from a fast rotator again, you would also have that stage, which might take longer perhaps than you estimated. But I just wonder, so how much angular momentum is imparted would depend in part by the impact parameter of the Stickney impactor, and did you consider that intermediate state that maybe you just increase the libration amplitude instead of going fully to a fast rotator situation?
What I calculated how much of a desynchronization there would be. I didn't take into consideration whether or not. I mean, if you have to ask the question, if one rotation every 2 or 3 orbits is in the range of a libration shift like what you're talking about or not, but we didn't directly look at that.
Next talk is by William Farrell. The title is Space Environment in Stickney Crater, a Dream 2 intramural study and the space weather associated surface weathering at Phobos. It's a very long title.
It's all right. I tried to go for the longest title. Yep. Oh, good. Thank you. Right. So as they get the